Hello, and thank you for attending my presentation. My name is Luke Dernach, and I'm with the Laboratory for Intelligent Decisions and Autonomous Robotics at Georgia Tech. And today I'm going to be talking about some of our recent work on developing robust trajectory optimization methods for robot locomotion when there is uncertainty present in our model of the terrain. Incorporating robustness to terrain uncertainty into motion planning could greatly benefit the development of safe, legged locomotion strategies for robots. Unmodeled disturbances from the terrain, such as abrupt changes in friction or occlusions in the height of the terrain, can cause robots to slip, trip, and fall. And while there are methods that can help the robots to get back up, methods for planning robust locomotion strategies are needed to avoid these failure cases in the first place. Planning techniques for robots that involve intermittent contact include recent works such as contact implicit and contact invariant trajectory optimization, both of which specifically include models of contact geometry and friction. These methods also explicitly include models of discontinuous contact forces and impulses, which enables them to produce dynamic robot motions without pre-specifying contact sequences. However, the solutions these methods produce are brittle with respect to uncertainty in the contact model, making executing them highly sensitive to discrepancies between the real and modeled contact properties. Several works have already investigated making trajectory optimization robust against uncertainty in the model parameters. Some works have first sampled uncertain model parameters, such as uncertain limb masses, and generated an ensemble of trajectories from which a single robust trajectory can be extracted, while others have placed confidence bounds on uncertain parameters such as friction, and then updated these bounds based on execution error. These works have required generating multiple trajectories, either offline before execution or iteratively with execution, to achieve some robustness. However, it's still unclear if each of the intermediate generated trajectories is robust to contact uncertainty. Along a different track are the risk-sensitive approaches, which propagate uncertainty from state measurement or the dynamic model to the cost function, and then minimize the higher order statistics of the cost. These methods can produce a wide spectrum of behaviors. For example, in the cliff rolled example on the right, where S indicates the start position and G is the goal, risk-sensitive methods can produce a risk-seeking behavior, shown in blue, which takes a short path edging along the cliff, or a risk-averse behavior, shown in green, which takes a wider path to avoid the cliff. And while the ability to produce multiple risky behaviors is impressive, these methods have yet to be applied to uncertainty in contact. In our work, our goal is to include models of contact uncertainty into trajectory optimization, and then develop risk-sensitive objectives which can produce a wide range of contact-robust trajectories. We aim to show that when contact uncertainty is present, we can produce trajectories which are robust to variations in the contact parameters, and that as the uncertainty vanishes, our trajectories approach those generated by the traditional, non-robust techniques that have already been developed. We build our work on the contact implicit trajectory optimization framework, as this methodology provides us with a natural model for contact. In addition to having the dynamics constraints and boundary conditions, the contact implicit method includes additional constraints governing contact. Contact properties are modeled through the contact distance function and the coefficient of friction, while contact forces are governed by a set of complementarity constraints. However, because these constraints encode a precise model for contact, the solutions this method generates are sensitive to errors and uncertainty in the contact model. To develop contact robust optimization, we first assume that the terrain parameters, that's the contact distance and the friction coefficient, are normally and independently distributed. We then replace the complementarity constraints with a residual function. As an example here, we replace only the constraint on non-penetration and normal force with a residual function based on the minimum. This residual function has the property that it takes its roots when the complementarity constraints are satisfied, and so we add it to the cost function as an exact penalty term. Finally, to account for the stochasticity in the model, we include the expected residual in our cost. This method is called the expected residual minimization technique, and it was first introduced to robotics by Yuval Tassa and Imo Todorov in 2010 as a technique for smoothing out the complementarity problem for contact. In this work, however, we're going to investigate its properties for encoding robustness to uncertainty in contact into trajectory optimization. Before we move on to the examples, however, there are two useful theoretical properties of the ERM cost that I'd like to tell you about. The first is that it decomposes into a mean and variance term, indicating that minimizing the ERM cost minimizes the sensitivity of the solutions to variations in the contact parameters. Secondly, as the uncertainty decreases, the ERM cost converges to the exact penalty cost using the mean values of the uncertain parameters, and so we can recover the original non-robust problem. We can see this convergence visually on the right, where, for instance, if the horizontal axis denotes contact force and the vertical axis denotes the contact distance, as the uncertainty decreases, the solution set to this minimization problem converges to the non-negative axes, which are the solutions to the original complementarity problem. In our work, we've tested the ERM approach in 3 examples. In our first example, we have to slide a block over terrain where there is uncertainty in the friction coefficient. In the second example, we propel a cart along a track by making contact with the ground, where the distance to the ground is uncertain. And finally, we have a hopper that traverses terrain where the height of the terrain is uncertain and where there is uncertainty in the friction coefficient. In our first example, we must slide a block over terrain where the friction coefficient is uncertain. We first compare trajectories generated with the ERM cost for uncertain friction to those generated without the cost, and then we evaluate the performance of the optimized controls from trajectory optimization in open-loop simulations, where we've also perturbed the friction coefficient. We assumed the friction coefficient had an expected value of 1/2, and we tested the ERM cost under several values of the uncertainty. Comparing the ERM trajectories, here shown in red, yellow, and purple, to the reference trajectory shown in blue, we found that the ERM cost increases the sliding velocity and reduces the time in sliding, but maintains the same friction force during sliding as the reference optimization, which uses the expected value of friction. By varying the friction uncertainty, we also found that the ERM-generated trajectories converge to the reference trajectory in a mean-squared difference sense as the uncertainty decreases. To evaluate the robustness of our method, we took the controls produced by the ERM and reference trajectory optimizations and simulated them over terrains where we varied the value of the friction coefficient from what we used during optimization. We also compared the performance of the ERM controls to controls generated by a worst-case robust scenario optimization, in which the optimization must solve for a trajectory that will still be feasible, even for the worst possible value of friction. In both these examples, the green line marks the desired final position of the block. The worst-case trajectory is shown in green, the ERM is in red, and the reference trajectory is shown in blue. On the left, we simulated the controls on terrain where the friction coefficient is lower than what we expected in optimization. In this case, the ERM gets close to the goal position, the reference trajectory overshoots the goal position, and the worst-case scenario control attains the goal position. However, we found that the performance of the worst-case scenario controls is due to the fact that the worst-case optimization solves for a trajectory that must respect the smallest possible value for friction. On the right, we simulated the controls on terrain where the friction coefficient is higher than what we used in optimization, indicated by the darker color in the terrain. Here, both the reference and worst-case controls undershot the goal, while the ERM achieved a similar position to what it had achieved in the low friction case and was the closest of the 3 to the goal. By repeating this experiment across a range of friction perturbations, we found that the worst case and reference controls produced trajectories with a similar spread in final position around the target position of 5 meters, but that the ERM controls produced trajectories with a tighter spread around the goal position. To us, this indicates that the ERM controls are more robust to variations in friction coefficient compared to the worst case and reference trajectories. In our second example, we have a cart that is constrained along a horizontal frictionless track and must propel itself by using a 2-link pendulum to contact the ground. Here we assume that the distance between the cart and the ground was uncertain, but that it had an expected value of 1.5 meters. As with the sliding block, we also tested different levels of uncertainty in the distance to the terrain and compared against a non-ERM reference. We found that the foot height increased with increasing terrain height uncertainty, eventually leading the foot to flip over, as shown in the red case, but that as the terrain height uncertainty decreased, the ERM trajectories converged to the reference trajectory, as was the case with the sliding block. In our final example, we investigated hopping over terrain with uncertainty in both the height of the terrain and in the coefficient of friction. In this example, the hopper also has 2 contact points, one at the toe and one at the heel. Here we also examined the effects of the ERM cost on the motion of the floating base as well as the foot. As with the cart, we found that the ERM trajectories produced higher foot clearance with increasing terrain height uncertainty. However, even though the base height is also free to move, the ERM cost does not increase the height of the base during hopping by a similar amount to how it increases the height of the foot. In this example, we also found that while the ERM produces higher hopping than the non-robust trajectory, it does permit some normal force to be applied at a distance from the expected value of the terrain, while the non-ERM trajectory does not, as the reference case must obey the strict complementarity constraints. In summary, we have tested the effects of including an ERM cost to model uncertainty in the terrain parameters into trajectory optimization. We found that the ERM produces behaviors which are contact averse. Costs encoding friction coefficient uncertainty reduce sliding time to avoid non-zero friction forces, and costs encoding height uncertainty increase the contact distance to avoid having normal forces. As the uncertainty decreases, however, the ERM trajectories converge to the optimal trajectories generated by traditional methods. And in our open loop simulations, we also showed that these ERM controls are more robust to perturbations in terrain parameter values than the worst case scenario optimizations or the reference controls. We believe our study marks an important first step towards reasoning about robustness to uncertainty in the terrain during motion planning, but that there are still open avenues for future research. Our ERM cost trades off between robustness and optimality as the uncertainty changes, but future works could develop methods to control that trade-off at fixed values for uncertainty, or could develop methods to update contact uncertainty information from data, which could lead to robust and adaptive replanning by adapting the uncertainty and robustness online from data as we execute the motion. Additionally, our ERM method produces only contact-averse trajectories. Future works could modify it to produce contact-seeking trajectories, which could also be useful for collecting data about contact. And finally, there are open questions about how our work scales up to more complex robots in full three-dimensional environments. And while we believe that the complexity of solving the ERM should scale only with the number of contacts, this has yet to be tested. With that, I'd like to thank my lab, my funding source, and the open source robotics toolbox Drake, which made my project possible.